That's us. That's what we're doing. So I'm giving you the link to that record of our conversations on chat, addressing to everybody. I'm giving you that link. So now you can click there, and I see quite a few already got it. The interesting thing is, I think that it wants even me to request access, and I think I know why is that. So let's go to another browser. That's Microsoft Compute, no, Google Computing browsers, but here we are, quantum computing. There you are. Okay, it's the same, but here I can edit. Okay, are we good to go? Yes? Let's see, I will open the chat and I will ask you this question, addressing everybody. Are we good to go? You can type, right? And I see somebody who joined just right now, so I'm giving everybody permission to talk. Okay, you can type and you're good to go. Thank you very much, Vijay. And let me see and let me show what I prepared for you guys. So this is September 8th, that's today, and we're continuing reading the Quantum Computation and Quantum Information book. I will tell you once again how amazing that is by Mike and Ike. It's not really Mike and Ike, but that's people who in the know call it this way. And what will come today is the Bloch sphere. I'll show you that, and the exercise. Okay, that's the plan. So I prepared the slides for you. The slides are right here. So if you click there, right, then you can probably open it like that. But I really prefer to download it if I can. And that means here, download as a PowerPoint. That's good enough. I might also have it on my desktop. Now download, good enough. Okay, now these slides, I updated them. So even if you have your old version, you will be doing good if you download and overwrite the previous one. And I added sectional qubits. But the whole slide deck is pretty good. So let me do this because some people maybe have not seen it. So it's a good idea. That is a background material, and that is actually the introductory slide deck for my teaching. So there was a show by people who are. So that's a nice show about quantum computing. And even though you may have a thing about this quantum bit, to me, it's still, by the way, it says my internet is unstable. If you see anything like that, tell me. Okay, so even though you have seen stuff about quantum bit, but at least I personally find it extremely useful to review it every time. So let's go and let's introduce this quantum bit again, and especially for those people who have not done it before. And again, there is John, and he needs an ability to talk. Okay, qubit. So we all know that bits are there. We're too familiar with them. We know all about them. That is what is maybe stopping us to understand quantum bits, and that is just because our logic doesn't quite work. So too, we're used to bits and it's our logic and it's very clear. But in quantum computation, we also have some kind of bits. And we usually, to start, we talk about electrons. So before we spoke about how people were able to catch those individual uh, physical particles and make them work. That was some work to isolate them, but now they've done it. So you have those physical things, and they will be representing your bits. So therefore, what is a qubit? Qubit, of course, is a quantum bit. But beyond that, we are going to describe it always as mathematical objects. And I maybe told you that I chanced to ask a friend, "What are you doing?" And he said, "Oh, I'm doing quantum computing." And well, it's a special friend from high school. So uh, he said, "I go away from physics as soon as I possibly can. I'm not into physics. I go to mathematics." Well, I'm not exactly doing that. Right. I want to always connect that to the physical objects, but that's a balance that we will all have to walk. So yes, we said that qubits are physical objects and that they can be represented by electrons or photons or ions, and I honestly am not quite sure about those particles. But practically, everybody will treat them as mathematical objects. To everybody, the qubit will be simply a vector. And just as a qubit is simply a number, it's either 0 or 1, and that is all it can do honestly. There's nothing hiding. Now, qubit is a vector, and there is a nice thing about that way of approaching the qubits. If they're mathematical objects, then they are the same. It doesn't matter what's the underlying physical representation. It may be electron, it may be photon, it may be ion. It's under very cold temperatures, but we will still look at them as a vector. So our vector will start from telling us that just like a classical bit, 0 or 1, the qubit will also have at least those two states. It's called 0 and 1. Now, that is an unusual notation, and that represents a particle that can be in the state of either 0 or 1, but don't worry, very soon we'll make it practical. But to denote the fact that they can be anything in between and quite anything in between, we'll show it as a what you would call pipe on the left and more than sign on the right. And those symbols are tricky to represent because in the books they usually represent by some kind of special character. But I find that this pipe and then 0 and then greater than works quite well in text and in converter that I'm using into slides. So these are the two possible states, but not the only ones. So it can be in these states, but it can be also anything in between. Now, before you ask me, how can that be? You can be anything in between. We will show you that you can take that same state 0 and multiply it by a number. You can take that same state 1 and multiply it by a number. So when this number is 1, simple 1, then you get 0. And when this number is 1, then you get a 1. So it's my way of representing a qubit that can be anything in between. And I wonder if could you say something like hello? Because I wonder if you talk and I don't hear. Hello? Can you say hello?
Hello. Can you hear me?
Hello. Absolutely well. That's amazing. Very nice. Thank you so much.
The
Okay.
qubits worked.
Yeah, yeah, that's amazing, right? I showed you the qubit and we started talking. Okay. So the qubit, I'll show you the physical representation because I think it's very hard to digest this kind of thing. Well, first of all, why Dirac notation? Well, that's because Dirac invented it in the 30s. But still, to me, I'm always struggling, and I'm struggling for a whole year with all of that. So the qubit can be a 0, it can be a 1, but it also can be a, a combination of 0 or 1. Now, the first way to explain this is to say that it can be 0 with the probability of alpha, or alpha sounds just like it sounds. That's easy. Or it can be 1 with the probability of, now that letter is a Greek letter, which I looked up the pronunciation, and it is vita. Okay, so alpha vita. Now that's a probability. In other words, very soon we'll say that those elusive electrons don't tell you exactly what state I apologize. There was some interruption in the internet, but we're back now. Now, let me go back to see if everybody is still enabled to talk. If they want to do that. Yes. Okay, very good. So sorry, but luckily the miracle of you have a backup internet on your phone. It worked. Okay, so we were saying that there is this 0 or 1 in the quantum world, but it can be anything in between. So that thing shows that each qubit can hold a lot of information because it can possibly be in any combination of these states. So potentially you have an infinite number of states because these are numbers. And then when you measure that, then it becomes at the 0. Okay, enough mystery. So we'll continue. We said these are complex numbers. And if you want to be very scientific, you represent your qubits as a linear combination of 2 states, but you multiply them by a complex number. Now, that also doesn't make sense. There are a lot of things that do not make sense, but gradually we'll just use them because we know they work practically. These things, 0 and 1, are called computational basis states because the real state of the quantum bit qubit is a combination of these. That's called quantum computational basis, but they are also, you can think of them as two vectors, like x and y. So that's not that bad. And we can examine, it can examine a qubit. The interesting thing is that even though we can examine a bit is easy to examine. We do it all the time in computer science, right? But a qubit, you can't really examine. It will not tell you what its state is because that's a philosophical question. Does it even exist, that real state? Or no, until we ask. But once we ask, it will tell you with certain probabilities that it's either 0 or 1. Therefore, quantum mechanics tells us that that is what you can find out about it. You can find out today, right now, is it 0 or is it 1? But other than that, it's hiding. Now, there are some limitations. We said it's alpha and beta, and since these are probability, a probability of that being 0, probability of that being 1, then they should come together and they be 1, right? There is a probability of one state, probability of state number 2, and together that should be 1. Why is it absolute value? And why is it squared? That's like this. First of all, we're talking about alpha being a complex number. So it has a length of that vector, and you can calculate the module of that vector. That is this absolute value of alpha. Now, the second thing is that it just so comes out of quantum mechanics that you don't add the probabilities, but instead you say when you square that, that's when you get the probability. So together this plus that is 1, because the probabilities have to be equal 1 together. Now, in this wonderful world of quantum physics, Richard Feynman, was the one who suggested, well, we'll set these probabilities to negative, and that's how the formulas will work. Not these are still normal. But in a certain situation, he said, let's make probabilities negative. He has that kind of view of mathematics. It should work for him. So how could it be negative probability? Again, the formulas give us that it works, that's right. And luckily, at least here, we don't go into the negative probabilities world. But we said that we can put any number here and any number here, and it will be a qubit. Well, here's a qubit. This qubit says that I am that much probability of being 0 and that much probability of being 1. Now, how much? If you take this, we remember that to get to the real probability, you need to square that. And if you square 1 over the square root of 2, you get exactly 1/2. If you square 1 over square root of 2 here, you get also 1/2, and therefore it's 1/2 and 1/2. In other words, this is a qubit in the state that it's maybe 50% when you measure it. When you measure it, 50% that will come out as 0, and 50% that will come out as 1. Wonderful. So now we have a way to represent our qubits by taking the basic state and either 0 or in zero connotation or 1, or any combination of this, and that's the combination that I'm offering you. All right, now let's go and look a little bit at what that physically is. This is electron, and it can have different levels of energy. The first thing that the physicists discovered is that it cannot have any level of energy. It can have only specific levels of energy. So if you think of electron as a wave, then it can be only specific waves. Specific wave has a specific level of energy. And when it goes this way, it is a 0, and when it goes that way, it is a 1. And that begins to explain to you why you are in any in-between state as well. So that's one way to think of your qubits. And another way to think of qubits is to add more math. That to me is a crazy formula, and I'll give you another crazy formula very shortly. But if you remember that cosine squared of anything, cosine of any angle is squared plus sine of the same angle squared is 1, then you understand why the preference for sine and cosine, because they can also represent probabilities, and squared this plus that gives you 1. Now, what is that? What is that amazing thing? Well, the first thing is that you need to know the Greek letters, and I don't. So I had to look it up. This is theta, okay? Theta, theta. I'll have to check theta or theta. Anybody knows? So let's say theta. Theta, just an angle. It will come later on, but right now that's just an angle. This is gamma, okay? And that is the physical constant that they will like to multiply by. But who needs this physical constant? As it turns out later on, to find out is it 0 or 1, we don't care about that constant, so we'll take it out later on. That's the real equation. Now, this is psi, and that's how you represent the real quantum of the real thing. That's one way. So I would be afraid of that formula, but don't be afraid because it works. That's cosine and sine. Now, another thing is this is a very interesting letter. It's called phi, right? Phi. And you take e to the power of phi. Well, you can take powers. You can take powers e to the power of phi. But what is this I doing here? I is imaginary number, if you remember. That is complex numbers. They have the imaginary part, and that goes more than your I don't want to say kitchen. Some people do complex numbers in the kitchen, but more than your regular common sense numbers. And how can you multiply it to the power of I? All right. So here we're going into the world of formulas. You can represent e to the power of anything by a series of numbers, infinite series, and stick I in there and something will work. But we'll take out this number, the one that was here. We took it out because we say it's not that important. And we remember every time we see this notation that we're dealing with the possible state of the qubit, and this one also possible state of the qubit. And as a result of measurement, we'll get a 0 or 1, and that will be our useful result. So with that little math, I'll give you a picture that will explain all of that. Here is a picture. That picture is called the Bloch sphere because the mathematician who invented it, his name was Bloch. That's why I'm pronouncing it with the CH being Ch. Bloch, not Bloch. And that is our theta. That's our angle. So you take our electron, which is right here, qubit in the state of 0. Right here, it's in the state of 1. So if you take that theta and you take that is initial state, it's 0, and move it in the direction of theta that far, that's what you get. That's a very important picture because we'll have to keep it in mind when we do our exercises. So you take the 0 and you move it in direction of theta. That's number 1 that you do. And number 2 is that you also move it along the y-axis by the direction of phi. Okay, so 2 rotations, 1 rotation and 2 rotation, and you get the final result. All right. Let me, no, that we don't go. That's exactly all theory. And now we want to do an exercise, a practical exercise. So let me do this. I'll stop sharing for a second. And I offer you a chance to say something. And I will share the screen again, and I'll give you an exercise. Now, to do the exercise, you'll have to go right here, and it will be lab from here. So let's go to this lab. That's the lab. I'm giving you the link on our class or seminar recording. That's the link that you have. Now, we need a very specific lab out there. We need this lab. Representing qubit states, it is called. And you know what? Let me show it to you first in the HTML form. Oh, pretty bad looking. Well, how about in the IPYNB form? It is at least a little bit better, but we are not going to do the whole thing. We'll go straight to the Bloch sphere right here. There you are. Look at that. Now, if you run this code, you will get this picture. So your exercise will be to actually, yes, run this code and see the picture. Therefore, let's go and do it. Now, you can do two things. You can download it here and then uploaded it to Colab, Google Colab. That's one way to run it. Another way to run it is to clone the lab. Last time I suggested let's start being real. Let's do lab clone. And I have already cloned the lab. So it is, in my case, it is here. So I don't expect that you will necessarily follow me here. No, that's not the right lab. CG quantum bit lab. That's all these same things that I showed you, they are here. So, but later on, if you want to try it, that's how you do it. And I have also downloaded all the Python packages and installed them. And since I do it under conda, then I can say conda activate Qiskit. So I do that only once. You'll have to do it once, attentively, set it up. Then after that, you just say Jupyter Lab, and it's live for you, and we're going to see how it works and experiment with that. Okay, it's open exactly on the right lab. And in fact, I'm not going to go through the whole lab right now, but I'm only interested in that Bloch sphere. So let's look at what is going on here. And then maybe if we can, we'll do the exercises, and that will be good enough. So what we do here is we import the math package because we need the pi number, 3, 14, 15, as you remember, all of that. So that is the number, and that's all we need. We need the math. Since we install Qiskit, then we import Bloch vector, and we don't need anything else. So let us run that. Running, you see the star, it's really honestly running. And there you are. Well, let's see how we can understand it, and then let us see how we can change it. So these are the coordinates. These coordinates are two angles. One angle that goes from 0 and another angle that goes from the y-axis. Okay, I see. Do you need any module to be imported to just math? That's all. Well, actually, there is something important. From Qiskit visualization, you import plot Bloch vector, but nothing else. you saw that I just jumped to that particular fragment of code and I didn't do anything. I didn't run it before. I started right here. Proof of the point. Well, let me do this. Let me go to kernel. Let me restart kernel and clear all output. Okay, nothing running. Then I'm going right to this place and I'm running just that one. And look, it worked, right? So that's all you need. You can even copy and paste it to another place and it will still work here. But we have rotated. Let's see if we understand why this little arrow went this way. Well, the first thing that we did is we rotated pi over 4. Now, pi over 4, 45 degrees, moves us from here to, if we're going from here to here, then it's in the middle. That we understand. But the thing is that we also rotated it in the negative direction from y here. Okay, so pi over 4 this way, and then pi over 4 this way. So in order to really understand that, we should play with these numbers. Therefore, what I'm suggesting is that let's copy this, take it out, and here I'll have to rely on your help. I'm copying this. So first we need to give it the radius as it says, then the theta, and then the phi. Very good. So let's rerun it. Rerun it. I just copied it. I didn't change anything. Nothing to change, and I did nothing change. Well, let's try to make a radius a little small. Let's say 0.5. Let's see if it works. Yes, it is smaller now. Look, it's magic, right? 0.5. Let's make it 0.1, real small. All right. So we see that that part works. What happens if I make it 2? Well, now, all of that doesn't make any sense. By convention, block sphere is radius 1. So we'll put it back to 1. Now, what I want to do, of course, is simple case. First of all, let's put that at 0. That means don't rotate from your 0 state. Let's see if it runs. Yeah, it runs. It says don't rotate from the 0 state. And if you don't rotate, then it seems like there is no change. We still rotate by pi over 4 in the negative direction, but since we are kind of spinning around our own axis, nothing changes. So here we can put, let's say, plus pi over 4, and nothing changes, right? All right, what else can we do? Well, let's try to do math pi over 2. So pi over 2 says 90 degrees, and indeed it went from here to this plane. You see, that's that plane. 90 degrees from here is here. And then in the positive, right? I changed it from negative to positive. In the positive direction from here, right? And only half of the angle, pi over 4. So let's move it to here maybe, right? For that, I think I need to do pi over 2. Let's try. Okay, we moved it this way and this way and that way. So what if we put 0 here? Amazing, but we see what's going on. So we go from here to here. So I suggest that if we take that, that's already 0. If we make that into whole pi, not tail pi over half, but whole pi, then we get exactly 1. Okay. Well, if that is what we can do, then let's try to do the exercises. And I have to confess, guys, I am not sure that I will be able to do the exercises, but you will help me. Okay. Now, we want to present qubit in its 0 state. What should it be on the Bloch sphere, and how do I give it the parameters? Any suggestions? Which angle do I need to give it here? We're forming 2 angles, theta and phi. Okay, so what's my theta and what's my phi? Any suggestions? Well, okay, both 0. Let's do it. Because we're not moving away from our 0 state. That's what you're suggesting. Bravo. Both 0. We did it. We are right here. Next, 1. Okay. Now I'm doing this. I'm saying use this amazing notation. How about that? And I give you the state, you give me the what? Theta and phi. Well, let me suggest this. I think we did it. We need to move it 180 degrees this way. And okay, theta is my pi and phi is 0 as ML. I'm not sure who you are, ML, but I would totally trust you. Okay, here we are. So it is math pi and phi is 0. Let's run. Exactly here. Math pi. In other words, let's go all the way 180 degrees, which is pi, right here. And this is 0. And we got exactly that. So now we know how to represent the 0 state and the 1 state. All right, that was a good warm-up, because now comes this thingy. Now, I'm not sure if I can even copy and paste that, but let us try. Amazing, yes. I don't think it completely correctly did it, but you see what I mean, right? You mean this. I could do this funny thing. I could, while you are thinking, I can try to make a pitch out of that. Okay. Okay. And then drop that picture there. That's a fun exercise. There you are. Well, doesn't help much, right? Screenshot. Of course, if I double click on that, you'll see it, but that's not needed for you guys because you see it. It's right here. 1 over the square root of 2 of that and that. So what are now your suggestions? So our exercise right now is 3, right? And obviously what we're doing is we're taking the X and Y notation and converting it to Y notation. So 1/4 on both. Well, let's try that. Here's the code. Well, it's something like what we started with. So over 4, you're suggesting, VJ, and that is math pi over 4. Let's run it. And there you are. So whether that is right or no, it's as much as you can draw, but we'll assume it's length 1 here. So it does go to the actual sphere, and it goes pi over 4 in this direction, and then pi over 4 in this direction. So guys, I just cannot tell you if it is right or wrong. It looks nice, right? So we'll have to believe VJ. I hope they would give us the answers. Into circles, and it's easy to visualize. That's what VJ says. They figured out how it will break each of the pi and theta. All right, all we can do, guys, is keep exercising, and it's this one. So 1 over square root 2 of 0 minus I times 1. Well, first of all, change plus to minus, and then multiplied by I. Let me try that. So that will be minus. I'm not even sure. No, we cannot do any kind of I here. Well, let's do it with a minus. That's kind of what we started with, right? It was this. And now I, it's probably 90 degrees along some axis, which would make it 3/4. But I'm not sure, guys. It's the kind of exercise you give to ChatGPT and verify. How about making this homework, right? Let's do this. Let's make a picture out of that. Like that. And let's put it for your homework. Well, right here, quantum computing, right? And what if I say this? Homework for you. And then I drop a picture there. All right. And that way, next time when we meet, you can show your results. You can show how you set it up. Yes, maybe 1 over pi. And so you said that I, VJ, how did you deal with I? I'll be happy to draw it here for you, but will that be right or wrong? That is something that you will have to prove to us. 1 over 4 pi we already have, and pi over 4 without even the minus.
Without even the minus, because it goes to the, so on the unit circle, 5 pi by 4, it takes a full circle and then comes back to the negative direction.
Full circle because of I, right?
Right, yeah.
Okay, wonderful. So here we are. Where is my lab? Here it is. Here's my lab. So you're saying that is still 4, but this is 5 times. So the picture will look like that. But yes, we will go through that again next time. And the last one. Now they're giving us another bigger problem. To show that you can represent your vectors in this way. No clue. Okay, great. I like that. That's what we should come to. That is quantum computing for you, or quantum physics. But I gave you the task for the homework. It was right here. Right? No, that's AI. It was right here. Sorry, here. Okay. So you will always be able to find it. The next time we meet, the mail will say desirable that you will do and explain how do it and explain it. All right. All right. Thank you very much. Now, what I usually do is I stop screen share, and therefore you get a chance to ask, talk, or just wish you a very good week. And see you next time.
Thank you. Have you in the past talked about the setup for the Jupyter notebooks and stuff like that?
I have, and what I will do is give you the setup. It's in this lab, but why don't we go quickly through that next time?
Okay.
But it is here in this lab, which you can find on our record. There is setup, and it says that's how you install Qiskit, and that's how you prepare for the notebook.
Okay. We'll try it
So
out.
we'll do it together. Yeah, try it out. Tell me the results. Maybe I will adjust it then when we go through all of that. We'll see, maybe something is easier than it should be. Maybe it can be updated, but I will go through that and help you explore setup.
Okay, thank you.
Oh, I'm not showing, but it is there. It's there.
Yeah, I'll find out. I'm
All
there.
right. Yeah, thank you very much. Be well.